Okay, so first thing that happens is you release the car. Question is, what can you determine if you release about the situation if you know A naught? Well, if you know A naught, then let's say there's A naught, you can determine the potential energy of the system here. Now, so this is the initial potential energy of the magnet system. Okay? If you know that, you can actually determine the initial potential energy of the entire system. If you also know theta and L and H. Okay? So, I'll just say, though, that okay, PE gets converted to kinetic energy, and some of the energy will be used to overcome friction. But of course things get complicated because this thing is, okay, if you're on a level of theta equals 0, well, that's what happens, okay? So by the time the car gets to the end here, we're going to assume that we're so far along here that the magnetic potential energy is essentially 0 at that point, okay? So we're going to assume that L is great enough that the magnetic potential energy at distance L is negligible. Okay? So what we can certainly say is that by the time you get here, there's 0 magnetic potential energy. So all the magnetic potential energy has now been converted to other forms of energy. Okay? Okay, so again, this gets a little bit complicated. We don't want to get into the details of analyzing this. But what we can say is we can determine the kinetic energy at the edge I'll say we can then determine the kinetic energy at the edge if we know theta, L, and mu k. Okay, so the question is going to be how, but you can think it through. You say, well, if I know theta, if theta isn't 0, if theta is 0, then how much energy gets lost between here and here? Okay, well, friction is going to drag on the car over the distance L, and part of your initial potential energy is going to go to doing the work to overcome the friction. Well, if we can analyze that much, then we know how fast the car is going here, right? Because we know the kinetic energy, we can find the velocity. So 1/2 mv squared equal to the kinetic energy, we get the velocity. So we can determine the kinetic energy at the edge if we know theta, L, and mu k. Then we have a projectile problem. Okay, whether theta is 0 or not, we know the initial speed, and we know the initial angle of the projectile, and we know how far it falls. So then we could determine x. So that's kind of an overview. We've got 3 phases of motion. We've got to figure out how much potential energy change we have here. Got to figure out how much work is done against friction here. If theta is not 0, we also have a potential energy change from here to here. Okay? Then if we need it, we have potential energy change from here to here. Maybe we don't need that. So there are at least 3 phases involved here. The projectile, the motion along the incline, and the initial potential energy. Okay. So you got to take care of those one at a time. So we can analyze these things one at a time. If we know the initial velocity and the angle, the velocity here and the angle, then what do? Well, we do what we do with projectiles. So that's something we've known, hopefully, for some time now. How do we figure out the work done against friction? Well, we know how far. If we got an angle, we've got to figure out a normal force. Multiply that by mu k, so we know how much force is being exerted by friction. So we can figure out how much work is done by the non-conservative frictional force. If we don't have an angle, we don't have any change in gravitational potential energy from here to here. If the angle's 0, if the angle's not 0, we do have a change in gravitational potential energy. Then a really neat problem that probably wouldn't put on the test. Don't ever trust me not to. Is figuring out how to maximize x by changing the angle theta. What angle theta do you maximize x? All kinds of things you can do with this problem. Well, we're going to break it down phase by phase, because what I want you to understand is, one, we got this problem here that involves a whole lot of the stuff that we've seen in the first 7 chapters. Okay, we got a projectile, we got friction, we got incline, we got potential energy, we got kinetic energy. There's more. There are things in those chapters that don't get involved here. It turns out, we could analyze the motion along here using equations of uniformly accelerated motion. Okay? And we're going to find that we like it a lot better if we can do it using energy. But I might put this on a test and say, okay, tell me what the equations of uniformly accelerated motion tell you, and then is that result consistent with what you get when you analyze energy? Okay. And since the most recent chapters are energy, we will emphasize the energy aspect, but there are variants of this problem where you might even want to use, I can't think of one, but I'm sure I could if I tried, where you might even want to use the equations of uniformly accelerated motion. Okay, well, that's enough basis that we can have fun for the next hour, okay? I think. And if we get through that, I've got plenty of others queued up. But I want to give you an example, again, of a problem. Okay, main idea. This problem is pretty comprehensive, and it can be broken into at least 3 phases. So you got to see how to break a problem down, and then hopefully have the technique to solve each of the problems that each of the sequential problems that you create. Okay.